got your homework you can turn in, but it's just Chem Activity 4, 24C. There is Mastering Chemistry due tonight as well. And I believe next week we have nothing due because the next activity is all interruptive forces, and we won't have learned anything yet. So you get a break on homework for next week. The lab that you did last week, you can turn that in next week's lab, since we don't have lab this week either. But I will be here Wednesday morning regardless, so if you want to drop by and ask questions while you're studying, feel free. All right. I want to point this out real quick. You're going to get all this on the exam. So that's all the equations. You got the electronegativities as well, although it's not moving very well. Thank you. It won't be in color, but you can read the little symbols down here: red, orange, yellow, green, blue, indigo, violet. Here's your nice little pictures of the cubes. So let's just go through these. If you don't have any idea how I got the answer I got, interrupt me. I'm going to try to explain them as we go. If you have any follow-up questions, you're like, well, what about this? Just ask, it's fine. Okay, so.
Oh, it's peer review.
Yeah, so this is the practice exam. All we're going to do today. So, at room temperature, CSF is expected to be what? So, we need to use the bond type triangle to answer this, right? This is 222. We need to look up electronegativities. So if I go back to this chart, CS is 0.66. Fluorine is 4.19. You don't really have to do anything here because this one's an extreme case. So CSF on the bond type triangle is most definitely ionic. This is the most ionic thing. All right, we don't even see it. It's the most ionic thing. So if it's ionic, what kind of properties it will have? It's not going to be a conducting solid, right? That's a metal.
Brittle?
It's going to be it's going to be a brittle solid basically. It's not soft. It is brittle. Salt is brittle. You can smash it. Yeah, it's brittle. All right. So D. Okay. Maybe I should. Let me see if I can do this. Insert. No, draw. Red. There we go. Brittle. Boom. No. Two finger? No. How do I get it to scroll without having to? Two finger? No. Alright, let's just turn the drawing off. Okay. A certain substance that is very, in PDF it works that way. That is very hard, has a high melting point, is non-conducting unless melted, is most likely to be. So not conducting unless melted is kind of the key here. This is like the most obvious part of it. For an ionic solid, right? Ionic solids are non-conductive. If you melt them, now you have these mobile ions that can move. I mean, that's the word mobile there. So we're talking about NaCl. So B. And everything else fits. So it's generally high melting points, generally pretty hard. It's going to be brittle, but it's hard.
Why is it not E? I know it's
So it's E would be conductive as a solid. So copper, and then melting points for metals are pretty variable.
Oh, okay. I forgot that part, but that was just because I'm muscle memory, and it didn't really work when we were doing it in the lab. The conduction on metals. So
Oh.
I'm just trying to remember it now.
Okay.
Like, that's how that is.
So like those little weird pieces didn't connect very well, or?
When we were doing the lab, we were trying to conduct all the different metals. I know the liquid metal didn't really want it, but the solid metal for sure didn't want to conduct.
Huh.
On ours, I don't know if it was.
Okay. Well. Okay.
I'll remember that though.
Okay. So which of these is the most metallic character? So for metallic, we are looking for middle of the road. Sorry, not difference. We want very middle of the road average electronegativity, but we want very, no, actually not middle, low average electronegativity, excuse me. Metallic, yeah, low. And for the difference in electronegativity, I think we want that to be fairly low as well. The more the larger the difference in electronegativity, the more ionic it's going to be. So we want low average electronegativity, and so you have to basically calculate all these. So tin with bromine, tin with phosphorus, tin with chlorine, tin with oxygen, tin with sulfur. This is going to be tedious. So tin is 1.82. And so what were the other ones? They were all up here. So we basically want something that is going to average out to low. We want another low electronegativity. So as low as possible. As close to 10 as possible. I forgot which one was the best there.
I think it's going to be P.
It's P?
Yeah.
Yeah. So it looks like P. All right. So 2.25.
No, you did that. Yeah. That's what
Did I skip one? No,
No, no, no.
great. There it is. So SNP seems like the phosphorus looks like it has the lowest electronegativity that compares with tins. So B. Number 4, diamond is an example of
C. Covalent.
network covalent solid. Yep. Can't say anything else about that. So predict which compound has a high melting point and is a conductor in the molten and aqueous states. So what they're describing is an ionic solid again. It's conductive when it's molten, and it's conductive when it's in the aqueous, which means that it implies that it's soluble in water. If it's aqueous, you can dissolve it in water. So that's not going to be a metal, all right? It's going to be an ionic compound. And so which one is the most ionic here? We want the biggest difference in electronegativity, all right? Ionic, large difference in electronegativity. So we're pairing aluminum, which is going to have a low electronegativity, with something that has a really high electronegativity, which on this chart probably is aluminum nitride. If you go look at the table of electronegativities, nitrogen is probably going to be the highest out of all those. It's closest to fluorine out of all those. So. All right, which is larger, the sodium cation or the chloride anion? So hopefully you would say the chloride anion is larger. Most of the time, almost always, the anion is a larger ion than the cation is. Right? Only when you do really extreme cases do you get a larger cation, like cesium plus might be bigger than fluoride, but I'm not going to give you those edge cases, right? Generally, the anion is bigger. Okay. So what would be the correct ordering of these substances from lowest melting point to highest? So we have ice, diamond, NaCl. I mean, I think it's pretty obvious that ice is going to have the lowest melting point.
Unless it's slang.
True. But no, even if it's the slang,
It still has a low melting point.
it's going to have a low. It's going to be an organic thing.
So it's
Ice
C.
slang.
Never mind.
Which drug is it? It's one of the.
I think it's meth. I think it's meth.
It's meth. Okay. Really? One of the drugs.
It's one of them, yeah.
So is it
See,
crack?
I don't know, different generations.
Okay.
Like this new thing.
No,
No.
it's old. It's all old 80s, 90s terms.
So it's C.
So between, it's going to be C in this case. So we look at NaCl and diamond. We're talking about ionic compounds versus covalent networks. And while they both have high melting points, covalent networks are always higher. Okay, they have much stronger bonds than ionic compounds do. Okay, so definitely C. Ice is a molecular solid. It's a polar one, but it's still a molecular solid which have low melting points. All right, a solid has a very high melting point, great hardness, and poor electrical conduction. That sounds like a covalent network to me. Very high melting point key, hardness good, no conductivity. They all describe covalent networks. This is different from an ionic compound because I think it's the very high is probably what gives it away. Okay, is close to being an ionic compound, but a covalent network fits this better. Metallic solids do not exhibit brittleness. Yeah, they are the kind of the opposite because they have such weak bonds that when you want to smash it into pieces, it won't do that. It'll just move out of the way, just rebond with their neighbors somewhere else. Pretty weak bonds. They just deform. So D, extreme brittleness, do not. Crystalline solids differ from amorphous solids in that crystalline solids have
patterns.
Yeah. So B, a long range repeating pattern of atoms, molecules, or ions. Crystalline solids have these repeating patterns. That's it. And amorphous solids do not. There's no pattern to how they're organized.
Oh, cool.
What fraction of the volume of each corner atom is actually within the volume of a face-centered cubic unit cell? 1/8. Why 1/8? Is because that corner is shared between 8 different unit cells. So each unit cell gets 1/8 of that atom. All right. Cesium chloride crystallizes in a unit cell that contains cesium at the center and chloride at each corner. The unit cell contains
1 and 1.
1 and 1. So we're talking, that's describing body-centered cubic, exactly. The center one counts as 1, it's only one in. The 8 corners each count as 1/8, that adds up to 1 as well. So 1 cesium, 1 chloride. And it's in the formula. 1 cesium, 1 chloride. Just to make sure that that's correct, you can look at the periodic table. Cesium is group 1, chloride is group 7, plus 1 minus 1. All right. So if I have a unit cell in this two-dimensional crystal, this is two-dimensional, so just let me repeat this pattern briefly. So if I just draw the unit cell part, which is right here, these corners count as a quarter. This is 2D, and that's because each corner is shared by 4 unit cells. 1, 2, 3, 4. This is 1 in the middle, so it counts as 1, and so there is a quarter, 4 quarters, 1x, 1o,
I don't think they were
1 and 1 again.
If you eat the
Sodium oxide crystallizes in a structure in which the oxide ions are in a face-centered cubic lattice, and the sodium ions are in tetrahedral holes. The number of sodium ions in the unit cell is. So this is just being familiar with what the holes in that face-centered cubic cell look like. So if I do the layer diagram, just to remind you, let me just do the face-centered cubic part. So here's Z is equal to 0, and the top layer 2. Here's the middle layer, which has the faces. So that's face-centered cubic. When your tetrahedral holes are completely filled, that means your quarter layer and your 3/4 layer is completely filled as well. So let me use solid colors here. And there's 4 positions here, there's 4 positions here. Those are all the tetrahedral hole positions. This is different from diamond. Remember, diamond only uses half of them. But this is a different one. It's telling you that you're using all of them. And they have to be all of them because if you count the white atoms, which we're going to count as the oxides, there's 4 total oxides those face-centered cubic gives you. Well, according to the formula, there should be double the amount of sodium. That's what the formula is telling us. So all of these tetrahedral holes have to be filled. You have to have 8 sodiums. 8 to 4 is 2 to 1. So there are 8 sodium ions in tetrahedral holes in this particular compound. All right, a metal crystallizes in a body-centered. You have a question?
Oh yeah, I was just gonna say, could you like explain this one a little more? Because this one I was super confused on.
This one that we just did?
No, 14, the one we're about to be on.
Oh, 15. Okay.
14, both of them. Yeah, 14 and 15 I was super
Oh, the one we just did. Okay. So the one we just did. I mean, so I guess I think when I said something wrong in that the problem doesn't tell us that the sodium ions are in all of the tetrahedral holes. They're just saying we've got sodium atoms in the tetrahedral holes. Well, I mean, is it like diamond where it's half and half like this, or is it where all of them are filled up? So if I count, so these are the oxygens. Oops, wrong way. And these are, what are they, sodiums. If I count up the total number of oxygens inside the unit cell, for the face center positions, there's 4 total ones. So there'd be 4 oxygens. And then for the sodiums, if it was like this, there'd be 1, 2, 3, 4, and that's it. So the formula would come out to be 4 to 4, or just 1 to 1.
Oh, okay, I get it.
Which is not the formula. And so for it to be double the amount of NAs, you need to have all of the tetrahedral holes filled up. To help, okay.
That's a lot to, okay, I understand it, yeah, that makes sense.
Yeah, so we learned the positions of the tetrahedral holes, and there are 8 of them possible. But then we moved to diamond, and we said, well, a diamond only uses half of them. So that's that specific case. Other compounds will use all of them, like this one does.
So most of the time it will be 8 if it asks you, except for with diamond?
It depends on what formula you need to be.
Is, okay.
So for diamond, so diamond is all carbon, so that's different, and diamond needs to have coordination number 4. That's how that works. But if you compare like gallium arsenide, you know, GaS, which is also which is zinc blende structure, right? Which is like diamond. That the formula is 1 to 1, 1 gallium to 1 arsenic, and so you have to only have half the tetrahedral holes filled up. But now here, this particular problem, the formula is 2 to 1, 2 sodiums to 1 oxygen. So you have to have all the tetrahedral holes used up.
Oh, yeah, that makes sense.
That way you get the right number. Okay, so 15.
Can I ask a question? I know
Yeah.
this is gonna sound like a little off topic, but now that we're on it, and I want to make sure. Do you know this formula?
What's the formula?
It's called something's limit to wavelength or something like that. I was just wondering if you knew about it.
Read it real quick.
Here you go. Photo equation. Do you know about that? Is that? I mean, that works.
I'm not sure where they get the number
That's
from.
what I was going to ask you about the number, but it works. I used it on the homework and on the band gap stuff, and it works every time. And it's just a simple division.
Oh, you know what it is? So the HC, instead of using Planck's constant, the one we know, 6.66.
Is that just all that equals?
Well, that's what Planck's constant is, and then speed of light is meters per second.
Yeah.
What they did is they multiplied those two numbers together, and then converted the units from joules to electron volts, so that you can just plug in electron volts and it'll work.
Oh, cool.
So that's where they got that number from.
Okay, cool. So it works. I mean, you. Right.
Okay. All right. A metal crystallizes. So this one we won't have on an exam. Okay. I don't know if you want me to do it still.
Yeah, we're not gonna.
Number 15?
Yeah. So we won't have this one on the exam because this one's calculating a packing efficiency.
We're not having anything calculating packing efficiency.
No. So so this is we can try it real quick just to make sure, but this may help you kind of visualize some other things. But a metal is in a body BCC cell, the edge length. All right, so let's draw kind of what we're showing here. So body center cubic, you got one in the center, you got the corners. You got the corners, by bad perspective. And the side. So one side is 2.00 times 10 to the 2, so that's 200 picometers. Assume the atoms in the cell touch along the cube diagonal. Oh my god. the percentage of empty volume in the unit cell will be. Alright, let's not do this one. This one's too much. It's all geometry. So basically we would have to compute the diagonal, and then from the diagonal, get the radius of the atoms, and it would be a big pain in the butt, so let's not do that.
So they have to read.
I think I do it
It's
on the
D.
key.
It's D.
Is it D?
Okay.
Yeah.
Yeah.
I'm pretty sure it's B.
So,
Since it's.
No, it's D.
It's space.
it's probably, oh, if I circled D, then I probably did it wrong, because it's the opposite. It's the percentage of empty volume.
Yep.
So what is
So,
it?
so this is a stupid question. This is like way over
So
overkill.
it is C?
So it's calculating packing efficiency and then doing the opposite. So instead of saying how packed is this, the question is how much empty space is left.
And the answer is.
So it's basically 100% minus the packing efficiency, which would I think be B, like you said.
Yeah, besides, you said something about.
Well, wouldn't that be C? Because
It's 68%.
68.
Sorry, C.
This
Sorry.
is how you gaslight.
That was
man.
correct. Because
Okay.
I don't think so. That's what I assumed.
Okay. I don't want to do this one because it's really just geometry. We would
Wasn't
be
there-
sitting here trying to figure out, well, how do you go from a side to a diagonal in 3D?
Wait, but I think it was actually not because it just memorized.
Yeah.
Because if I
That's what I
remember.
was gonna say.
If you memorize the
Well,
packing efficiency,
there's just three because there's one for each. Like.
yeah.
It's
Packing
not that hard
efficiency
to
is
remember.
60.
If you memorize the packing
74,
efficiency,
32.
that works. You do not have to memorize the packing efficiency, but yeah.
That's why. That's why I
100
assumed.
minus 68, yeah. Okay.
Yeah, it took me a bit of time, but I remembered that,
I
so
didn't do it, I
it's
just
entirely
memorized
pointless
the
question.
thing.
Well, it's
All for it.
it's an extra credit question. Let's put it that way.
Wait, I got it. Shit, wrong.
All right.
So
So we're gonna skip that.
this is
But
C.
you
I
don't
was
need to do the
correct.
calculations is the problem.
I get that though. If you can do it in your head, you're sitting there going, "No, let's do it."
I don't want it to be a geometry problem, so we're not going to do it. So in the molecular orbital model of benzene, the 6 p orbitals combine to form how many molecular orbitals? 6. It's just the basic rule is however many atomic orbitals you mix together, you'll get the same number of molecular orbitals.
I got an anxiety now.
So, in the unit cell of sphalerite, zinc ions occupy half the tetrahedral holes in a face-centered cubic lattice of sulfide ions. The number of formula units of zinc sulfide in the unit cell is, well, that's a difference. Yeah, it is 4. It's slightly different than the way we've been talking about it, but what they're doing is describing zinc blend, right? The zinc blend structure. So it's 4 from the sulfide ions, which are in the face-centered cubic
Yeah,
positions.
I should automatically assume that.
Half the tetrahedral holes have zinc ions, so we're talking about this. And if you count the atoms 4 and 4, the formula is ZNS, so there's 4 of these formulas inside this unit cell. Zinc 4, sulfide 4. So 4 formula units of ZNS inside this unit cell.
Which one is benzene again?
Benzene.
What's the symbol?
That, yeah, so there's a lot of ways to draw this. There's this, or this, or really it's just that.
Oh, wow.
So that's benzene. These are all the same thing. That's the line drawing. That's the version that instead of putting double bonds and single bonds, we just put one giant double, multiple bond in the middle. So that's what benzene is. And the idea is you've got sigma bonds between the carbons and the hydrogens. These are orbitals that are pointing directly at the other atoms. They overlap, and those make localized bonds. But each carbon is sp2 hybridized. So it has one p orbital left over that's kind of pointing in and out of the board. They're all parallel to each other. And so these p orbitals do these side-to-side overlap. And, you could say, well, these 2 carbons are doing a double bond, these 2 are doing a double bond. But in Lewis structures, we would write the resonance, the other form of this, where the double bond is moved over one spot. So which 2 carbons are making the double bond? Well, the reality, none of the carbons are making only a double bond. These p orbitals are all kind of overlapping each other, and we can show an MO diagram that kind of shows like what kind of bonding it does. So these 6 p orbitals will combine together, and your new MO diagram will kind of look like this. So the 6 p orbitals make 6 MOs. These are bonding MOs, these are anti-bonding MOs. And there's 1, 2, 3, 4, 5, 6 electrons in these. So that's kind of what the MO diagram of the p orbitals of benzene kind of look like. So bonding, anti-bonding, the bond order would be 6 minus 0 divided by 2, 3. There are 3 bonds, total bonds, distributed through this pi ring, the ring system that the p orbitals make. Yeah, so that's in the book. I think that was brought up in the workbooks a little bit, but it's definitely talked about in the textbooks. We briefly mentioned it when we talked about MO theory at the beginning.
I have another question.
Yeah.
So what is the anti-bonding MO like?
What is it actually?
Yeah.
Um.
I'm having trouble like wrapping my head around it. Kind of.
So it is. I guess it's hard to kind of explain.
Is it just like a concept that kind of explain other things? I guess?
It is an energy state that you could have electrons exist in, but at that energy state, the electrons are somehow, and this is what's hard to visualize, they're somehow destabilizing the bond. So instead of adding to it or doing nothing, they're doing the opposite, they're destabilizing it. So an anti-bond is just a way to destabilize that attraction between the two atoms.
Okay.
Yeah.
I kind of don't want to ask this because I know
Yeah.
that it's just going to go in a whole other world. But
Uh-huh.
isn't there different types of electrons?
Yeah,
that's what I was saying. Like I didn't want to really ask this question.
I'm not positive there are other
Like
than
spin types or something like that. I mean,
Well,
is there habits to basically these electrofields? But like, why is it so necessity to always consistently always have the negative and the positive?
You mean the electrons are negative or
Or no, just the polarities.
Because that's just how the universe works.
I understand that. I understand that.
So the phase of the orbitals.
Yeah.
So, I mean, here's the thing. It's hard to kind of so it's easy to think of the electron as a particle.
Mm.
That's doable in our brains, I guess. But how do you perceive an electron which has mass as a wave, where it's not in one place, it's spread out? And that's what makes it harder to kind of visualize like what's going on. And so when you talk about MOs, molecular orbitals, we draw pictures that show these regions of space, but that's kind of where the electron, not always necessarily where this point particle electron can fly around in, but it's the waveform of the electron. So like, how do you imagine that wave? How do you imagine like when you think of a wave of light, you don't say the wave of light is like here. You say it's a ray.
Yeah.
It's a So it's hard to visualize. It's hard to kind of really pinpoint what that means physically. We don't really have that. As far as I know, nobody has come up with a good visualization for it that puts together both of those concepts into one. And that's what makes quantum mechanics hard. So you kind of have to rely on the math. And the math shows that this is what it does.
Mm.
So we have to kind of rely on that.
No, that's pretty cool.
Yeah.
Of course, to everyone outside of that, it looks just like nonsense numbers and symbols.
Yeah, yeah. What's
So-
up?
Is it not like a field, electron field, and you're just predicting where they are likely to be in the field?
I think that is the thing, yeah.
It's a little of both. I mean, what are we imagining? We're imagining a model of the atom. Like, hey, I can't see anything, but how am I going to visualize it that makes me understand how it works? And you could imagine it as a little point particle. You can imagine it as a field. Are they the real? Is that really how it is? I don't know if you can just say that's how it is, but the way that we are thinking about it fits with how it behaves, and so it's it's fine to think about it that way. So like, it's hard to say that this is how it is. Like, it's just this fits the math. It fits how it behaves. So let's continue thinking about it this way. Yeah, like. When we see an electron, like I think the closest I won't say the closest. When we see an electron, either we see its effects as it like passes through a bell jar in a vacuum, and we see it glow pink. Like, we don't see any image of electrons. We just see kind of what happens as it's moving. Or when we see atoms, we see the result of what they look like in bulk form. The closest we've gotten to seeing atoms is feeling them. Like, we actually can drag a tip that is atomically sharp over a really flat layer of atoms, like in a gold surface, and like we can get that tip to kind of trace the bumps of the atoms as it goes by, and we can see that tracing. So we can feel the repulsion of the atom with the tip, making it move up and down. But that's as close as we got to seeing what an atom looks like. Like, what does it really look like? I don't know. But we know that it repels the tip, and it does it like as if it was a ball, But like, we don't have any concept of knowing exactly what it looks like.
Besides, the way we see things is one of those particles.
Yeah.
So it's kind of impossible to visualize, period.
Yeah, we're getting to the realm of how reality works, I think. But I know it's frustrating. I have a hard time trying to teach that. Oh yeah.
It's just the way the world works.
It's just the way the world works.
And you just sort of forget about that.
You could find all the answers to the universe. You still got to do your laundry. I mean, at the end of the day, it's really kind of what you make of it.
I mean, the standard model of physics, of particle physics, which is kind of how every single particle in the universe is made, which includes how protons, how electrons are made, what are they made of, like all the quarks, the things that make up these things. I mean, even that is based on experiments where they smash things together and they see what kind of particles come out, what energies they have. And only recently they had to revise with the boson wave because there was an error in the experiment, which is going to throw things out the window. So I don't know. It's changing. Our models right now seem to fit. They seem to work with reality. They let us. So a model is only good if it lets us predict things. And that's the point of an experiment. We want to learn how something works. Why? So that we can predict other things.
They're reliable tools.
Yeah, so
they've worked
these
for hundreds
tools
of
work
years.
for these things. We're going to keep using them. We're going to assume that they work. That's how the reality works. Until we find something that doesn't work anymore, and then we have to change our model.
A 16-mile-long superconductor. Oh my gosh, that's so cool.
Okay. You're still looking at particle accelerators?
Yeah, I'm looking at what you just talked about. Yeah.
Okay. All right. So by the way, particle accelerators, if you're not familiar, they are these giant tunnels, miles long, and they have to evacuate them, have no air in them. And that's already a major. How do you do that for this giant loop? And then they're filled with high current. I don't know. I think they're loops that are connected, but basically, you're generating a magnetic field that can turn on and off like that. So as a particle is flying by, you can turn on the magnetic field, attract the particle closer to this ring, and then immediately turn it off, so that when the particle goes through, it doesn't go backwards again. They just keep accelerating the particle until it reaches supermassive speeds, and then they get another particle going the opposite direction. They slam them together, see what happens. Takes a lot of effort. Costs a lot too. All right, a certain metal fluoride crystallizes in such a way that the fluoride ions occupy simple cubic lattice, while the metal atoms occupy the body centers of the half of the cubes. This is a weird one. So the formula for the metal fluoride is what? So they're not really giving us the full unit cell. They're kind of describing what the crystal looks like. And so they're saying, well, if I look at it, some of them have the pattern where they're just plain old simple cubic. And then others, the other half, have this pattern where the fluorides are still in the simple cubic formation, but, and I'm forgetting one more in the back. Hold on, let's do that. But half of them have an atom, a metal, that's in the very center. So let's say that this one has a metal in the very center. So, you know, these are the 2 unit cells I find in my crystal. Half of them are like this, half of them are like this. What is the formula going to be? Well, let's just count total atoms for both of them. And so, in this unit cell, I've got 1 total, what is this, fluoride, 1 fluoride, right? 8 corners. Each of the corner counts as an 8, so that adds up to 1. In this unit cell, there's 1 fluoride and 1 metal, whatever that metal is. And so if I combine these 2 pictures, half of them are like this, half of them are like this, there's going to be twice as many fluorides and only 1 of the metals. So A is the answer for this.
That is really confusing to visualize.
Yeah, I don't know why that wasn't easy to. It's not easy to see.
I mean, I guess just kind of try to, draw it out, or
I think it's
use
just
layer
yeah.
diagrams if you have to. But the idea is there are 2 different kinds of unit cells in here, and so half of them are the top way, half of them are the second way. And so on average, there's going to be twice as many fluorides as metals. All right.
Oh, because that's the way it's describing. Oh, that is a really weird way to describe it. Okay, yeah.
Yeah. So like, yeah, if I were to, you know, this is not the, we're not drawing the proper unit cell of that crystal, because the proper unit cell of the crystal would be 1 unit cell, and then that would repeat and create the same pattern. This is a weird way of doing it because we don't have that, we didn't learn those other crystal systems. So this is another weird one, but you know, this is one, and we wouldn't have this one like on an exam, but this one should be not too bad. If you have the cations or the solid circles, how many cations are in the unit cell? Well, there's only 3 here, and they're inside the unit cell. They're not on an edge, they're not on a face. They're drawn inside not a box, but they're drawn inside the hexagon. So there's 3 cations in the unit cell here. Yeah, question.
My biggest thing for just like the shape is I didn't know what, like for the hexagon, I didn't know what like to count the side pieces. Like I mean like the ones on like the middle, because like not really the middle, like just like the side.
Like these maybe? Or?
Yeah, but like only the middle ones. I didn't know if they counted as space or corners.
Oh, like this one.
that's-
Yeah, okay, well, yeah, so this is why I wouldn't put it on a test, but if you think of a hexagon that kind of, it's you know, it's going to have this shape. That's the best I can do. So that's the shape it has. That atom in the center there is in the face right here.
So with
And
those,
it really can only be shared with one other unit, like one that's directly on top, and that's
so
it.
Now with the corner atoms be like divided like would be like 112. We count as like.
Oh yeah, so that's a different one. So these corner atoms, yeah, so if you draw a hexagon flat,
Yeah, that was like kind of confusing. I just didn't know if you count them as corners or like faces.
so we just keep going a little bit. So here's a corner,
With 1 second.
and if there's, you know, there's 3 here, but then there's the 3 that are on top. Right, so this is the bottom layer. There is a top layer over here, and that's also 3 different unit cells. So yeah, they're shared by 6.
Okay.
And so they count as 1/6 in this particular case.
Wait, it's gonna be 112 because there's like six on the top and 6 on the bottom. Like how
So there's 3 in the top and 3 in the bottom. So there's, so for instance, this unit cell right to this corner right there. It's got one more in front here, one more to the side here, like these are, and then it's got the bottom layer, the layer just underneath here. So there's 3 down there too. So there, we'd have to draw. I mean, I think it's some
Oh,
actual
yeah,
models.
There's 6 on top, then 6 on top. There.
Well, okay, so each corner, this is a corner,
Uh-huh.
counts as a 6th.
Okay.
Because there are, it's shared with 6 unit cells.
Sure.
And so how many? There's 1, 2, 3, 4, 5, 6, plus the top layer, 1, 2, 3, 4, 5, 6. There's 12 corners,
Uh-huh.
and the 12 corners count as a 6, so the corners count as 2 in this case. 12 times a 6th is...
Why is it different than like the cube, when you make a cube? Why is that? I guess that's what's kind of confused me. Like, why would this shape be different than the cube?
I mean, it's just however many it can be nearest neighbors to. So this, I need to get a model to really show you, because I don't have one for this, but this corner right here, which is right there, if I imagine this layer, like right here, there's a hexagon that fits right there, and there's a hexagon that fits right there, and that's it.
Mm-hmm.
But then if I go one layer down, there's a hexagon right underneath this one, plus another one and another one. So there's 6 unit cells that share that corner.
Okay.
And so because only 6 share the corner, each corner counts as a 6th. And there are 12 corners, so it just happens that the corners count up to 2.
Alright.
This is a face. That counts as a half. That's a face, so that's another 1,
Mm-hmm.
3. And then we have 3 inside. There's 6 there.
Okay.
So there's 6 anions in this thing. And so there's 3 cations to 6 anions. If the anion has a charge of -1, then the cation has to have a charge of +2 for this formula to work. All right, you need to have twice the number of twice the number of anions. And so if the cation has a +2 charge, you'll get a ratio of 1 to 2. All right, that's a hard one. So the answers here again just is 3 for cations, 6 for anions, and the cation has to have a charge of +2 for this ratio to work. So whatever the cations are, the cations, we counted up 3 of them. The anions, we counted up 6 of them. This simplifies to 1 to 2. And so if the anion has a -1 charge, then the cation must have had a +2 charge for that ratio to work. All right, crisscross rule. All right, this question, don't worry, that won't have a hexagon on the exam. But the basics, the concepts are the same. So what is the formula for the following unit cell? Well, this is FCC, the big atoms at least, and there are atoms in half of the tetrahedral hole positions. So that zinc and that zinc are in the top half. This zinc and this zinc are in the bottom quarter, top quarter, bottom quarter. So we're seeing this basically. Only half of the tetrahedral holes are occupied, and so the ratio, the formula is going to be 4 to 4 or 1 to 1.
I was kind of confused. Did they also tell us it's
I know, I was like, did they tell us the answer?
They tell us it's zinc and.
It tells you the answer.
Yeah.
So-
It tells you the answer. Okay.
It's okay. You
It's
did
not
that,
a very good
You
problem.
did that on one of the labs where I was like sitting there and I didn't get like her answer, and I'm sitting there trying to figure out on my own, and then I just looked down and it would just tell you the answer on the next page.
Okay. So as packing efficiency increases, coordination numbers
Increase.
also increase. The more neighbors you can have, the closer packed together you are. What is the coordination geometry around carbon in a diamond? It is tetrahedral. Right? All the carbons in diamond are tetrahedrally bonded. This is the nice question here. 25, which of the above shows sigma bonding? sigma bonding, first of all, sigma means an end-to-end overlap of orbitals, or another way is an overlap where there's only one place where your orbitals overlap. And the only ones that do bonding and not anti-bonding is number 1 up here. So this is a sigma bond between two s orbitals. And it's bonding because there is electron density between the two atoms. This is actually the sigma antibond. It's the two s orbitals overlapping and canceling each other out where they overlap to make 0 electron density. We're kind of emphasizing the 0 electron density line with that dotted line there. So 1, sigma bonding. Which of them shows a pi bonding? So pi is when two orbitals overlap, and they overlap in 2 different spots. Or it's a side-to-side overlap, if you want to imagine. And that's this one here, V. This is when you get the original p orbitals, and they go side to side. These 2 lobes add together, these 2 lobes add together, and you get the bonding overlap here. 2 is the opposite of that one. It's when the 2 p orbitals overlap and cancel each other out. That's the antibond. The only other thing left on here, which we haven't talked about, is this one. And this is actually another example of sigma bonding. The p orbitals are oriented where only one of their lobes overlap each. But when they overlap, it's antibonding. They make a region of 0 electron density between them. That one's sigma antibonding. So that's sigma antibonding. That's sigma antibonding as well.
Wait, what? Oh, you pushed it.
So yeah, which of these shows pi antibonding? Pi antibonding is just number 2.
Okay. Alright, cool.
Wait, so sorry. One
Yeah.
of them is sigma antibonding and the other is pi antibonding.
So this one is pi antibonding because this comes from 2 p orbitals, and they overlap in 2 different spots, above and below. But in this case, they cancel each other out, so they antibond. This is sigma antibonding because it's only 1 spot. This is also sigma antibonding. So there's 2 of them. The existence of an antibonding molecular orbital is explained by the fact that we use wave dynamics to talk about electron probability. Yeah, question?
I was just asking, like, waiting for the question, like, for this one, like, when I did, I only chose B. Would you give, like, half points for that? Like, if you just, like, you knew one of them but you didn't know the other?
So I guess so. These are my favorite type of questions, but I mean, A and B both fit. So we have to first understand that electrons or at least the
That's
clouds
true.
are wave dynamics. They're described because of wave like we treat the electrons like a wave, and the fact that, well, now that we think of them as waves can have opposite phases which can combine destructively, which is the one you need for antibonding molecular orbitals. So 2 of the above are true technically. Antimatter has nothing to do with anything. That exists, but that's not part of what we're talking about. Okay. And if you feel wrong on your test when you get it back and correct it, just bring it up. It's fine. A semiconducting solid solution used in manufacturing LED has the zinc blende structure. And this chemical formula, what are X and Y? So, what does this all mean? Well, remember when we make an LED that has zinc blende structure, it has to be isoelectronic with a group 4 element. It has to have that average of 4 valence electrons. It's kind of what we've focused on. So, do what I did before, kind of label these. Which group are they from? Are they from group 3, group 5, whatever? So aluminum is from group 3, gallium is from group 3, arsenic's from group 5, and phosphorus is from group 5. So we have a series of group 3 elements, a series of group 5 elements, and the rule is we need 1 atom of each. 1 of group 3, 1 of group 5, And so if I have a quarter gallium, I should have 0.75 aluminum. And if I've got 0.6 phosphorus, I should have 0.4 arsenic. So A is the best answer here. Those fractions need to add up to 1 each.
So AL and GA needs to add up to 1 and AS and P needs to add up to 1?
Yeah, because they're both from, so AL and GA are both from group 3. They have 3 valence electrons on average. So the rule, yeah, for us, one total atom of group 3, 1 total atom of group 5. So that ratio needs to be perfect. Okay, so we have these isoelectronic semiconductors. They have the same unit cell length and internuclear separation, same idea. Which isoelectronic solids have the largest band gap energy? So, you know, we have the electronegativities here, which is a clue. So difference in electronegativity, the biggest difference will give us the largest band gap. All right, and if you remember, but germanium has a band gap that emits a photon somewhere in the IR region. It's not visible to us, but when we start swapping germanium out for gallium and arsenic, now we start getting higher energy photons. It starts becoming visible. It starts to become reddish. And I don't know what zinc selenide is, but it's going to be higher energy than that even. And that's because we're getting a bigger difference in electronegativity, more ionic character, and so there's going to be a bigger band gap as a result. So C. Okay. 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 The molecular orbital model for germanium shows it to be a conductor. No. Well, we can look at the periodic table and we can see that it is definitely a semimetal. It's in that region. So it's not a conductor. It's not an insulator. It is a semiconductor. So why is it a semiconductor? Because the gap between the filled and lower and empty higher energy bands is relatively small, or because the gap is relatively large. So it's C, right? You need that band gap, the region, so the filled band, which is the valence band, and the empty band, which is the conduction band, that gap needs to be small. Not nothing, but it needs to be small. If it's too large, it's now an insulator. So C. All right, blue LEDs, what are they made of? So that's assuming that all of these are visible spectrum. Let's assume that they're all visible. This is kind of from the lab, so it's not one of those that I would give you in this context. But look at the difference between all of these. We're going from arsenic to phosphorus to oxygen, sulfur, nitrogen. Some of these are not isoelectronic with group 4. Some of these are not diamond or zinc blende crystal structure. So oxygen is 2 steps over from germanium. Gallium is only 1, so this is not even isoelectronic. Neither is gallium sulfide. So the only ones that actually are isoelectronic with the ones we've been talking about are gallium arsenide, gallium phosphide, gallium nitride. So what is the difference between them? Well, gallium nitride has the smallest bonds. Another way to think of it is it's going to have the largest difference in electronegativity. For both of those regions, we're going to create a larger band gap with gallium nitride. And the larger your band gap, the higher energy photon is released. And if we want high energy color, that's the blue side of the spectrum. Okay? So blue is higher energy than red. Alright, as you go to the blue side, the violet side, ultraviolet, that's higher energy.
So it is D?
It is E.
Oh my God.
E is most likely going to be the blue LED. And it is. If you look up in the lab, that's the one that's blue. Which we haven't done yet. But it's in the examples too. Alright, number 33, inorganic compounds that are semiconductors have an average of 4 valence electrons. Yeah. That's kind of what we're assuming. There's going to be exceptions, of course, but that's what we've been looking at. Those are the common ones. Assume all of the following are semiconductors that produce light ranging from red to blue. Well, this is almost exactly the same as the other question with the gallium nitride. Which of these represents the MO band diagram for a blue LED? We want the largest gap. The largest gap in band gap. Yes, eventually it's going to be an insulating thing, but until it becomes that, these are all produce visible light. This is most likely going to be the one that produces a blue LED. Highest band gap creates the highest energy photon, and blue is the high energy side of the visible spectrum. Okay, that's more reddish. That's probably IR even, although it does say it's visible, so probably red. All right, which one of these is not valid? That is true. It is A. It's not valid. So how do we know A is not valid? Well, gallium is group 3. Nitrogen is group 5. Arsenic is group 5. Well, I've only got half of a group 3 atom. That's it. And how many group 5 atoms do I have? I've got... Oh, it's not even written correctly.
I was wondering that.
If I plug in any number for X, if I plug in 0.5, it won't even work. So, yeah, this doesn't work. Basically, we want to vary we want to vary elements that are both from the same group if we're going to vary them. Like this one. Indium is group 3, arsenic is group 5, antimony is group 5. If we vary these amounts, that's fine. We're still going to average one group 3, one group 5. Yeah, I think this would work better if this was an X here. Or, no. It's just written weird. A is bad. The rest of them work. Even this one does. Because that's group 3, that's group 3, that's group 3. And that adds up to 1. And that's group 5. Yeah. And there's one of those too. Okay. Semiconductors are used in LEDs to produce variable wavelengths of light because the molecular orbitals overlap allows for electrons to move to the conduction band with 0 electron volts energy added. That is not true, right? So the idea behind a semiconductor is that there is a band gap. There is a certain amount of energy needed to cross from the valence band to the conduction band. And if the band gap is 0, then it's not a semiconductor anymore, it's a metal. So that's not true. In a semiconductor, the MO orbital overlap will create a little bit of band gap. So there's not a 0 electron volt energy added. I have to actually add energy for the electrons to jump up here. So that's not true. Insulators have band gaps, which are large at room temperature, but upon cooling, they can efficiently excite electrons to the conduction band. What do you think? So we know that insulators have large band gaps, but what happens when you cool the atoms in any structure? They slow down, they can get closer together, and what happens to orbital overlap when they get closer? What happens to the band gap when atoms get closer? So the orbital overlap's better, and so the band gap's going to be even larger.
Yeah.
So it's not going to be suddenly conducting when you cool it down. It's going to be worse.
So that's actually one of the questions that I had about the homework on the master chemistry. It just so semiconductors, when they talked about it being at room temperature, they always showed that there was electrons that were just going to the conduction band on their own because of the temperature.
A little bit.
A little bit.
So
that's a normal state though for semiconductors is what it was trying to say.
Mm-hmm.
Okay, and so why is that? Why is it that just room temperature enough is enough?
Well, room temperature, that's some thermal energy, and there might be enough to promote a few electrons up to the conduction band, depending on the semiconductor. It makes it slightly conductive, maybe not conductive enough for,
And that's why I'm just going to go on another limb real quick, but I'm assuming that that's why computers and certain types of processors have all different cooling needs and things like
Well,
that?
So, as far as I know, and I'm not an expert in this, they use semiconductors as a switch. So the idea is when they energize a circuit in one direction, they're like, okay, we send power through it. That's providing energy to your semiconductor. And then the semiconductor will allow a different circuit to conduct because suddenly it's conductive. And you can turn that pathway off by removing the energy to your semiconductor. So that's how semiconductors work. They're an internal switch, and so you can do logic with switches in a circuit board.
That's cool.
And that's where the ones and zeros come from. Before we had vacuum tubes, which I really am not exactly sure how this works either, but.
Or number C.
Oh, I forgot. Oh, sorry. So B is incorrect as well. C, the band gap can be tuned by substituting atoms in the crystal structure to alter the unit cell size. Yeah, you can make a solid solution out of this and change the band gap. So that works. Upon exciting electrons in metals, high energy light is released outside of the visible spectrum. So that's not true. Metals have zero band gap. So when you give a metal some energy, there is no there's no big gap drop of electrons from one state to another. Yeah, no, it doesn't work. So there's no good answer here because nothing really fits. You have to answer. Oh, it's true. C is the only one that's true. Yeah, okay. So C is true. All right. Sorry, I was thinking that it was which ones are false. Anyway, number 37. We have a band gap. What is the light emitted? Okay, that's an easy one. We'll do that one. Doesn't take much to do that one. So we want to convert our electron volts first to joules. And the conversion is 1 electron volt right there, 1 times 10 to the minus 19 joules. I feel like the conversion is getting more simplified as we go along, but this is good enough. This is not a great conversion, but it'll work. There is the energy in joules, and then for energy of a photon, Planck's constant times speed of light over wavelength. I'll rearrange for wavelength. 6.626 times 10 to the minus 34. Speed of light. And then finally the energy. So joules go, seconds go, and we're left with meters, which is going to be at 7.36 times 10 to the minus 7. And in nanometers, it's, I mean, you can see it, it's 736, but it's 1 times 10. Oh, let's see, this is meters, right? So 1 nanometer is 1 times 10 to the minus 9 meters. You get 736 nanometers. Okay. There's that one. So A. What color is that?
Red.
Red, yeah. You don't have to know this, but you can look it up. Okay. All right, let's do, this was annoying to do on the board as well. I'm going to have to flip screens quite a bit, but here we are taking 4 of these compounds here. Some of them are elements, one of them is an element. And using the bond type triangle to kind of determine what kind of solid it is. So there is the third, there's in the third column in here is what is the bonding based on atom type. This is basically the 151 old school idea of, well, what kind of compound does it make? Based on if it's a metal with a nonmetal, if it's a two nonmetals. So that's the naive way of understanding what kind of compound it is. And then once we figure this out, then let's compare it to what the bond type triangle says. So let me do a little table on the board here so I don't have to flip back and forth so many times. We've got CO, we've got Al, As, we've got copper and zinc, and we've got carbon diamond. So our difference in electronegativity, our average electronegativity, and then we have our bonding version 1 and bonding version 2. I'm just going to write that for now. So let's go back to the very beginning. We're going to look at the electronegativity table.
Is that going to be provided on the exam?
Yes.
Okay.
Yes. Okay, so quickly, carbon and oxygen, 2.54 and 3.61. The difference between them, 3.61 minus 2.54, is 1.07. Subtract one from the other to make it positive. And then the average, you add them together, 2.61 and 2.54, divide by 2, 3.075. Let's just do them all real quick. So after this, aluminum and arsenic. Aluminum 1.61 minus arsenic 2.21. Make it positive. So it's 0.6 for the difference. And then the average, 1.61 plus 2.21 divided by 2, 1.91. So copper and zinc, 1.8 and 1.6. The difference is 0.2. And the average is 1.7. I can do that one in my head. That one's easy. Carbon. The difference with carbon and itself is 0. No difference. And the average is, they're all 2.54, so the average is 2.54. Alright, now that we know that, let's find a bond type triangle to play with. And whoever is watching at home is going to have to imagine this because I'm going to use the projected thing on the board. But we're going to plot these numbers on the bond type triangle. Let me see if I can fit this better. Oh, that sucks. Alright, well, here, you know what? There we go. There we go. Alright, so, carbon monoxide. The difference in electronegativity, 1.07. Somewhere right in the middle here. And the average, 3.075, is right around there. 0.07, yeah. There's CO right there. That is definitely smack dab in the middle of the covalent region. You need to know what regions you switch. This is the covalent region. So we didn't actually do the element prediction, but this is a nonmetal, that's a nonmetal. That tells me covalent. The bond type triangle agrees. It's covalent. Al and As, aluminum and arsenic. Well, aluminum is a metal. Arsenic is a semi-metal. And I really didn't talk about too much about like what kind of material that makes when you combine semi-metals with things. But usually when you combine a metal and a semi-metal, you kind of make a semi-metal again.
On the sheet, it said like it was not a semi-metal.
What did it say? Ionic maybe? Or
yeah,
metallic?
so it was weird. I was like, well, kind of like a few of them had like a slash between, like some of them were like both, and that was
yeah. I fixed those on the actual exam too, so there's
Okay.
should be clear ones, and the ones that are not clear, it's I've given you the answer instead.
Okay.
But this is, so this is a prediction based on what kind of atom it is. You could call it metallic, you could call it semi-metallic. It's a weird one, okay? But what does the bond type triangle say? 0.6 is right here. 1.91 is over here. Yeah, pretty much semi-metallic. You could call it a little bit covalent maybe, but it's pretty much in the semi-metallic region. Al and S. Copper and zinc, two metals, probably metallic. Looks like an alloy. Does that agree on the bond type triangle? 0.2 and 1.7. Ooh. That is actually a semi-metal according to the bond type triangle. So when I mix these two metals, it makes something semi-metallic. Oh, we said this is semi-metallic too. So this is a weird one. This is one that's not what we would have predicted from basic ideas. Two metals don't actually make a, unless I calculated something wrong, but two metals don't actually make a metal.
It's so weird.
Okay. Now, did I do anything else wrong? No, I don't think so. Diamond, 0 and 0.254. 0 is down here, 254 is right around here. So there's diamond. That's pretty covalent. And we knew that to begin with. Okay, so that's not too hard. It's just being able to calculate these two numbers, plot them on the bond type triangle, and understand what region you're looking at. So please try to make sure you get the right line. Take 30 seconds to make sure you're graphing properly. Okay, here's another one. That is possibly on the exam, something like this.
Skipped a few.
Did I skip something?
Yeah.
Oh yeah, you're right. I'm sorry. Well, you skipped a bunch. So B, I guess, use the bond type triangle to determine whether there is an electronegativity difference above which a compound can always be predicted to be ionic. So is there a delta En where you can always say it's ionic? Well, if it's here, can you say it's always ionic? No, it could be covalent here.
Wouldn't it be like 2.9?
Or, yeah, so it'd have to be like way up here, 2.9 or so. Above 2.9, then it's definitely ionic. Use the bond type triangle to determine whether there is an electronegativity difference below which a compound can always be covalent. I think for this one, the answer is no, because I can have any one of these values as low as I need, and as long as the average electronegativity is, in this region, I've got something that's not ionic, or something that's doesn't fit. So, all right. 39. The following compounds are ionic. Only order them from lowest melting point to highest. This was like on the quiz. Oh, and I've got to give your quizzes back. I've got them. So, lowest to highest. Well, lowest is going to be, well, first of all, let's rank them according to their charges. So charge is going to affect melting point the most. Something with a +2, -2 charge is going to have the highest melting point. Something with a +1 and -1, +1, -1 is going to have the lowest melting point. This thing is got in the middle. Potassium's +1, but oxygen's -2. So that's going to be the highest. Then comes this. Between these two, the lowest melting point is going to be for rubidium iodide, because now we have to compare sizes of atoms. The larger the atoms, the worse the bonding, and the lower the melting point is going to be. So it goes RBI, lowest, then LIF, then K2O, then MgO.
No, yeah, well, electrical volt. But it throws the entire thing off.
Okay.
Yeah.
Let's see. Do you want to do this one? Sure. Okay. This one, the way it's asked, won't be on the quiz or the exam. But essentially what this is asking you to do is go backwards and go from not a density, but something like a density, and so maybe we'll do one with density, but go backwards and find what is the radius of an atom of lead. So how are we going to do that? Well, we are given something kind of like a density. It's the volume per mole, kind of the opposite of a density or inverse of a density. And so what we want to do is find the number of lead atoms per unit cell. Well, that's not hard to do. If we know it's face-centered structure, face-centered cubic, and it's just lead atoms, there's going to be 4 lead atoms per unit cell. Right? Face-centered cubic has 4 lead atoms. So for A, there's going to be 4 atoms per unit cell because it's FCC. Well, what is the volume of a single unit cell in picometers cubed?
Will you give us the equations for the volume for all of them?
So I'll probably give you something like this, like what you see in the front here. So notice I don't give you the volume, but I give you the side.
That's what I meant.
And then you can take the side and cube it to get the volume. Yeah.
That's what I meant.
I need to study that.
Okay. But let's write this down just in case we need it later. So the side for FCC is radical 8 times R. We'll come back to that. Oh, we skipped that. Hold on. There we go. So, what is the volume of a single unit cell? Well, I know that the volume is going to be side cubed. If I know the radius, I can get the length of a side. I don't have any of that, but I do have the molar volume, which is 18 cubic centimeters per mole. And maybe you guys don't know what molar volume is. That's fine, but look at the units. The units are cubic centimeters. That's a volume. Once I know the volume, I mean, that's what I'm looking for. I need the volume. Can I get the volume directly from this? Well, this is saying that if I have a mole of lead atoms, I will have 18 cubic centimeters worth of lead. That's how much space it'll take up. Well, the unit cell only has 4 atoms. So what if I get the volume for only 4 atoms? That will give me the unit cell size then. Does that kind of make sense?
Why wouldn't you divide it by Avogadro's?
Well, that's what ultimately I'm going to do. I'm going to convert per mole to per 4 atoms, because then I'll have the volume for just the unit cell, because there's only 4 atoms in the unit cell. So let's convert the moles to atoms. And when I do that, I will get 18 over 6.022 e to the 23. 2.99 times 10 to the minus 23 centimeters cubed per 1 atom. Right? Per atom. So that's over 1 atom. So I know the unit cell contains 4 atoms. So if I multiply this by 4 atoms, I will have the volume of a unit cell. And so that's going to be 1.20 times 10 to the minus 22 cubic centimeters. Okay, so I'm almost there. I've got a volume. That's the volume of the unit cell.
Sorry, really quick.
Yeah.
Why? I feel like you should. I mean, I feel like I would have, like, if you didn't do this, and was on the test or something, I would divide by 4 atoms, because it says, like, this is the 18 centimeters cubed per mole for the FCC structure of the solid lead, so wouldn't you have to divide by 4, because it's saying, like, that's the whole thing?
Well, I guess, I mean, if you look at what the dimensional analysis, what the units are saying, I've got this thing called the molar volume, which says the volume per mole. To get rid of the per mole, I can use Avogadro's number, and now I've turned it to per atom. So it's a 2.99 times 10 to the minus 3
Oh.
per atom. So, like the way the units are written, it literally means for every atom I add this volume. So if I have 4 atoms, I will have 4 times this volume. And that's ultimately what we're calculating. We know the unit cell contains 4 atoms, and so this is approximately the volume of the unit cell. Now that I've gotten there, let's do a practice on converting using cubic units. We don't really do that much. So I would like to go from centimeters to meters, and then meters to picometers. That's the easy conversion for me. I'll write these down. 1 centimeter is 10 to the minus 2. 1 picometer is 10 to the minus 12. But these are not going to work as is because this is centimeters cubed, not plain centimeters. So if we cube the whole thing, we will get the right conversion. So this becomes 10 to the minus 2 cubed is 10 to the minus 6 meters cubed, 1 centimeter cubed. This becomes 1 picometer cubed, 10 to the minus 12 cubed is 10 to the minus 36. I did that right. Yeah, 12 times 3. Yeah. Trying to make sure that I'm doing this right in my head. So that's the conversion. So 1.2 times 10 to the minus 22 times 1 times 10 to the minus 6 divided by 1 times 10 to the minus 36, and I get a pretty large number, 1.2, 5, 6, 7, 8, 1.2 times 10 to the 8, I think, picometers cubed. Anyway, that's the volume of a single unit cell in picometers cubed. Yeah, that makes sense. Okay. Okay. Picometers are tiny. They're smaller than the size of an atom, okay? So that's why that makes sense. All right, so what is the radius of a lead atom? Okay. So this is where we go now backwards here. Let's go from volume to the length of a side, and then once we know the side, let's go to the radius. Which volume am I going to use? Well, we want the radius in picometers, so let's use this one. Why not? So this is the volume, which is equal to side cubed. So how do I get a side? Do the cube root. And if you guys don't know how to do cube roots in a calculator, the cube root is the same thing as the x power to the 1/3. So that's how you do square roots. Square root is power to the 1/2. Cube root is power to the 1/3. So if I do this to the power of the 1/3, I will get just plain old sides. 1.2 times 10 to the 8 to the power of 1/3.
He just saved my life.
So the side is 493 picometers. That's the length of a unit cell side. Now let's go backwards. Let's get the radius. The radius is equal to the side divided by radical 8. So 493 over radical 8. This is a lot of math. And I get 174 picometers. So that's approximately the radius of a lead atom.
Did you say there's not really going to be like this one on the test? There's going to be just
Well,
density?
So this feels like a very.
I would expect to start from density rather than molar volume. So,
Okay.
the problems we've practiced, like on the quiz, make sure you can do it that way, going from length of the side or radius to a density, but also going from density backwards to a radius or something like that. Right? You can use molar mass. You can use all the other stuff that you need to use when you do this kind of problem. So yeah, I am not going to use molar volume. We haven't really talked about that, but I think the concepts are some of the concepts are the same. Okay, so now we've got this structure, and since this is mostly cubic, this is not the weird hexagon. So you know the rules, even though it's a weird looking one, you know the rules for how everything counts. This is, I think, a legit one to see on an exam. What would the formula of this thing be? So,
Hey, wasn't that the extra credit?
it is not.
It was not.
No,
That was quite different.
this is a little less complicated, I think. Well, probably equally complicated. So this is where it's tricky, and having this will help because you need to understand which ones are corners. That's a corner, but that is not a corner. It is an edge. So this is a corner of one of the cubes, but it's the edge of the entire unit cell. Okay. You could even, if you wanted to make this a little easier, you could do half of this and then just count it double. But let's just take it as one huge thing. So for the white atoms, these are corners. Those are corners. Corners count as an eighth, and there's 8 corners. So you get 1 atom from all the corners. That's a face. You can see it right here. That's a face. That's a face. You can see them here. And here. These are faces too. Sorry, I forgot those. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 faces. So these are all faces here. That's a face. There's 10 faces.
So that's like 2 people of each other.
Yeah, you can think of it as 2 of them, but just think of it as one big unit cell for now. So there's, how do you say, 10 faces? Faces count as a half, so half of 10 is 5. So I'm up to 6 white atoms right now. That one right there is a central atom. That's this one right here. It is only in that one unit cell, so I get 7. And these are edges. And edges count as a quarter. So 1, 2, 3, 4 edges times a quarter is 1 more, 8. So there's 8 of these white atoms. 8 seleniums, that's what the legend says. And then we look at the rest of these. Copper, 1, 2, 3, 4. They're all inside the unit cell. So they all count as 1 each. 4 coppers. Indium is the exact same. There's 4 of them, and they're inside. That is the number of atoms inside the unit cell. And so the formula of this thing would be the simplified formula. Would be 4 to 4 to 8, 1 to 1 to 2. 1 copper, 1 indium, 2 seleniums. That's the, we call it the empirical formula.
Sorry, can you explain again how there's 8 S8?
So there's a whole bunch of different ones. So there's these corners.
And they're each a quarters?
They're an eighth each. Corners are always an eighth in a cubic crystal system. So 8 times an eighth is 1. And then we have let's count the faces. So there's this 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. They're all in faces, and if these are hard to see, you verify using the layer diagram their faces. So 10 faces count as a half each. 10 times a half is 5. So I've got 6 total atoms now, 1 from the corner, 5 from the faces. That white atom here is right here, this one, that is right in the middle. That counts as 1 by itself, so I'm now going from 6 to 7. And then these are corners, not corners, excuse me, these are edges. These are on the, like where in the middle of where the 2 faces meet. And edges count as a quarter. Right? We did a lab where you saw those edges on other examples. And there's 4 of them. So 4 times a quarter is 1. So that's 8 total white atoms if you count them all up. Okay. How is this related to zinc blend? Well, it kind of looks like 2 zinc blends stacked on each other, but kind of one twisted the other way. Right? So notice that these are not the same. They look a little bit the same, but this black one is kind of in the, let's see. Yeah, this one's in the back, this one's in the front, but up here, they're kind of, oh, they switch sides. There it is, yeah. So you need 2 of them to make a whole unit cell. But they basically look like 2 zinc blend structures. Alright, draw the Z-layer diagrams for zinc blend. Hopefully you've seen that so many times you can do this. But zinc blend is FCC with half the tetrahedral holes filled. So you need 4 of these squares to show it. This is 0.25, this is 0.5, this is 0.75. And we've got our corners, the bottom layer and the top layer, and the face. And then in the middle layer, we've got our faces here. And in the quarter and 0.75 layers, we've got our tetrahedral holes. Only half of them, not the other 2. And 2 of them here, not the other 2. That's zinc blend.
Did you say this is like an extra protocol?
This one here, the 42, no, that's normal.
Or 41? Oh, 41.
I think that's something you should be able to do, because we know the rules for the cubic stuff. We've done the lab for it. The only additional thing that was in the lab was the edges, which is they count as a corner. We saw that with sodium chloride, the octahedral holes kind of thing. But other than that, it's just slightly more complicated cubic stuff. Here is, I think, a better one for what I was talking about, like this kind of problem. So you have a bar of an unknown metal. You find the density, it's 10.5 grams per cubic centimeter. And how do you do that? You can just weigh it and then dunk it in water and see how much volume it displaces and calculate it. Pretty easy to do. If we do X-ray diffraction on it, and we get a crystal structure, the unit cell happens to be 409 picometers in length, and it happens to be face center cubic. What atom is X? What is it? So how, what's the one property of an element we could use to quickly identify what element it is?
Atomic number?
Close, but atomic mass. So if we could figure out its mass, atomic mass, we would instantly identify what it is. And that's actually something we can figure out from this. So what is the atomic mass? It's usually grams per mole. If we can get a grams per mole value for this, we could pretty easily find what it is. So we've got our density, 10.5 grams per cubic centimeter. And basically we need to convert this volume into moles. Really, that's all we're doing, converting this volume into moles. So how are we going to do that? Well, if I know the unit cell volume, I could get rid of that. Let's see, how are we going to do this?
Would you do?
Let's find the unit cell volume. Yeah, go ahead.
I was gonna say, would you just convert 409 pm to centimeters, and then since it's an edge, it's like the same as a side. So
Yeah.
you divide by √8 to find the radius of this cubic.
Well, so if this is if the 409 is the edge of the unit cell, we don't need to use any of the fancy
it'll
formulas.
be
It's just going to be the sides cubed, and it'll give us the volume. So let's do that. Let's convert 409 picometers to centimeters. And that should be 4.09 times 10 to the minus 8 centimeters. I've done this a few times. And then let's convert that length, so that's the side of a unit cell. Let's convert it to a volume. So we're going to take that number and cube it, because for cubes, cube the sides and you get the volume. Somewhere over there.
So the way to the negative 18 or negative 8?
Oh, I'm sorry, 8. Excuse me. So 4.09 times 10 to the minus 8 cubed is 6.84 times 10 to the minus 23 centimeters cubed. So let's think about what this means. That is the volume per unit cell. So if I really want to do dimensional analysis, I can set this up. I could say 0.684 times 10 to the minus 23 centimeters cubed. That way that cancels. Per unit cell. That's the volume per unit cell. And let's just get the answer for this so we know what that means. This is basically 10.5 times that, 7.18 times 10 to the minus 22. So the centimeters cubed is gone now. Grams per unit cell. So for every 1 unit cell, that's the mass. Well, we don't want grams per unit cell, we want grams per mole. Well, let's make this a little bit easier. Let's first convert the unit cell into atoms. How many atoms in a unit cell?
Is it a phase one again?
It's face-centered cubic.
So
four.
So 4. There's 4 atoms. Notice my dimensional analysis still works. So, but let's keep going. We don't want atoms. I want moles. How do we go from atoms to moles? Avogadro's number, yeah. So we want moles down here. We want atoms to go away. For every 1 mole, there's 6.022 times 10 to the 23 atoms. And that's it. So divide by 4 times 6.022 e to the 23. This is 108 approximately grams per mole. What does that look like? Oh, doesn't exactly fit super well. But looks like, oh, it looks like silver. Silver is 107.86, 108. This looks like silver.
In statistics class, that's close enough.
If we had better values, we could be more precise. But yeah, this molar mass matches silver, so it's probably silver. Okay, and then finally draw and label the MO diagram for O2. I warned you guys, or told you guys, that you don't have to draw these out from scratch yourself. So most likely you'll see an outline of what what you're supposed to build. So for O2, you have your oxygens before they make any bonds. And that's kind of what the diagram will start off looking like. And these oxygens come with 6 valence electrons each. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And then when we bring them together and make a bond between them, these will overlap and make a bonding MO and an anti-bonding MO. These will overlap. 6 total atoms, orbitals. Will make 6 molecular orbitals. And oxygens is going to look like this: a bonding, another bonding, an anti-bonding, and another anti-bonding. So, label-wise, just kind of showing where these come from. Sorry if the lines are a little big. So this line here is your sigma bond from your s orbitals. This is your sigma antibond. We use a star to denote it, from your s orbitals. This is a sigma bond from your p orbitals. These are, I'm going to draw this a little better. These two are pi bonds from your p orbitals. This is your pi antibond from your p orbitals. And this is your sigma antibonds from your p orbitals. Those are the labels. Now, what do we do with, oh yeah, question.
Well, I have actually 2. First, shouldn't you also have the 1s bonds first?
If you need to, you can, but generally for MO diagrams, you only need to show the valence orbitals.
Doesn't usually, aren't the pi bonds, isn't pi bond usually after the 2 sigma?
So for oxygen and fluorine and neon, this is the way it is. For boron, carbon, and nitrogen, yeah, they're swapped.
And then my last one, I'm getting really confused, like on like how, because like with lithium, like
Uh-huh.
sometimes, even though it says like you only should have, like 2 lithium should have 2 valence electrons, yet sometimes we have them both at 3, and like then it's kind of, like for these, for the like MOs, like it's like sometimes we give them 3, and it's like I'm always kind of confused. Yeah.
So, if you're just showing the valence orbitals,
Mhm.
and you're showing what happens to the valence orbitals, then you only count valence electrons.
Mhm.
So for lithium, it would be 1 valence electron each, and you would just show the 2s, and that's all that matters.
Mhm.
But you can also show the inner electrons too, the inner orbitals. So you could do the 1s and the 2s, and then you have to count all the electrons in lithium. So lithium has 3 total electrons.
So yeah, like someone might be like a bond order diagram. I don't know which one to use because I've seen both done.
Well, so this is where you have to pay attention to what your starting atomic orbitals are, and pay attention to maybe if there's any labels on these. This is labeled. Comes from the 2s. So if you're only looking at valence, or origin, or orbitals, then just count valence electrons, and that's it.
Alright.
But if you see more than that, you see a 1s, then you do all the electrons. But so, let me just reiterate, on an exam, none of this would be labeled. You would have the little bars, or not the bars, the lines where the MOs and the atomic orbitals might be, but that's it. So you'd be expected to know how to label everything, where to put electrons, and then finally in the middle, so this oxygen came with 6, this oxygen came with 6, 12 total electrons. We're going to put them in the middle here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And that's the MO diagram for O2. That's it. Everything's labeled. Everything has electrons in it. I'll be honest, this side and this side are not as important, but they're just to kind of show you what the 2 atoms look like before they made the bond. That's all they are. Just kind of a comparison. That's it. But what do we get from this MO diagram? Well, this oxygen molecule is paramagnetic because there are unpaired electrons after you make the bond. So once you have your MOs formed, there are a pair of electrons which have no downspin to go with them. And so this is definitely paramagnetic. If everything's paired up, doesn't matter if they're full or not, as long as everything has a spin up and spin down together, then it is diamagnetic, but that's not the case here.
Quick
And-
question then.
Yeah.
So something like neon would be diamagnetic then? Or is that?
Yes. So neon, yeah, and neon in this case is just make 1 atom. There's no bonds it would make.
Oh yeah, right.
But as an atom by itself, it is definitely diamagnetic. What's weird is nitrogen as an atom by itself is definitely paramagnetic. It has unpaired electrons. But it comes as a molecule, N2, and the molecule is diamagnetic.
Okay.
Yeah. So, what else can we do? Well, let's say we have O2 minus. So O2 minus. This is called superoxide. If you are a biochem person, superoxide was, at least in the 90s, I don't know if that's changed, or early 2000s, they were like connecting it to lots of health conditions and stuff. Superoxide is like the reason why people think antioxidants work so well in the body, things like that. But research has changed probably since then, so I can't say much. But anyway, O2 minus, or O2 minus, how can we tell if it exists? Well, that minus charge means 1 extra electron. And so all I'm going to do is modify my current MO diagram to show the extra electron. One of these oxygens came with an extra electron when the bond was made. And so that extra electron, I have to put it in the lowest energy orbital possible. That's there. And in that case, what does it do to the bond order? Well, let's actually divide by 2. So we count up the number of electrons in bonding MOs. 1, 2, 3, 4, 5, 6, 7, 8. That's it. These are the bonding MOs.
What about the one? Why didn't you count the one that's
Up here?
No, like the second.
This one here? Because this is an anti-bonding MO.
Oh.
So yeah, pay attention to which ones are labeled with the star or not. Also, antibonding MOs are generally higher in energy than the original antibonding MOs that made them. So notice this was made from these two, and it's higher in energy. So that's where the second number comes in. Antibonding MO electrons, that's these two, plus 2, and a third one here. So there's 5 total antibonding electrons. 3 over 2 is 1.5. So it does exist. It does exist because it has a bond order, and that is not 0. And it's weaker than regular O2. Regular O2 is a bond order of 2. Double bond. But once you add the extra electron, it weakens the bond. So it's weird. Sometimes adding electrons strengthens the bond. Sometimes it weakens it. In this case, it weakens it. So, does it exist? Yes. As long as the bond order is greater than 0, it's going to exist. Oh, and we're done. We've reached the end. Sorry, that was painful. But there is not a lot. We haven't gone over a whole lot. Honestly, I mean, you see a lot of repetition in these questions. It's just a few different skill sets to learn. All right, one is getting to grips with telling what kind of bond you have based on electronegativity and all those things. Then looking at understanding properties based on information, like what kind of what kind of bond it is based on properties. Is it hard? Is it got a high melting point? And then band gap. Understanding the different solid solution formulas. What works and what doesn't. And then some calculations. So, yeah.
On that orbital diagram,
Yeah.
I don't know if I just see 13 electrons.
Well,
Okay,
so
I just want to know how it.
yeah. So there should be only 12 for regular O2.
Yeah.
But then the question C is, well, what if O2 minus existed?
Gotcha. I missed that.
Which would be exactly the same as this, just one extra electron.
Okay.
Which came with maybe that one or that one, doesn't matter. So. All right. Yeah. See you guys Wednesday. Please try to bring Scantron. They sell them at the bookstore, packets of 5. Can't exactly give them away freely anymore, but you can buy cheap Scantrons. They are anybody have any? They're the ones that have 50 questions per side. They're like the high density ones, really skinny rectangles. So we'll need a Scantron for half of the exam, and the other half we'll just write on the exam directly. Just makes grading easier. And if you don't have a Scantron, that's fine. We can loan you Scantrons, which you can pay back later when you buy something. But anyway, you don't forget about it if you can't find it. I don't have anything else, like per se. There's always, you can go back into Mastering Chemistry and do a lot of the problems over again. They won't give you credit for it, but you can do those again. There's back of the book problems that have, for the odd ones, usually have answers in the back of the book. Although I think I should be able to quickly tell you what the answers are if you need them. I think most of the connectivity stuff, I think you guys are doing, so I don't know if there's much more there you can do.
The Mastering Chemistry that's due tonight, is that on there?
Is it, sorry?
Is like the like this MO diagram and anti-bonding on there?
Oh, it should be in the Mastering Chemistry. There should be examples of that.
And then what would be that because I know exactly like those that equation right there.
Which particular equation?
Just that whole jumble.
This thing here?
Yeah.
So I can like look at them.
Well, there's no. Like I
What
didn't
are you
use a
solving?
specific equation, so what I did was I took the density
Uh-huh.
and crystal structure information,
Mm.
and I solved the radius of the atom. Like I figured out how big the atom was based on the unit cell dimensions that we got from crystallography,
Mhm.
which is and the density.
Ah.
So we have a density, we have unit cell dimensions that give us a volume,
Uh-huh.
and then we can get and the fact that there's 4 atoms per unit cell, we can get a molar mass from that.
Alright, cool.
And-
Thank you.
Sorry, I didn't mean radius, I meant molar mass. But yeah, we're identifying what the thing is.
Okay, thank you.
Yeah. You could get radius too.
So the extra time, so we can do it in your class, or we have to go in the testing center?
So if you're just gonna do a little bit of extra time, it's fine if you wanna do it
I don't
here.
think I'm gonna do more than like, I don't know.
Yeah, I mean, if
20
it's like,
minutes or something. I
yeah,
don't
if it's
know.
gonna be a lot longer than
Usually,
that.
like, remember last term I didn't do it long. that
Okay,
long.
you're probably okay.
Okay.
I'll let you know if you switch next
Okay,
time.
Okay. And then I'm just having like a lot of trouble understanding this entire.
The MO diagram stuff?
Yeah, and like the anti-bonding stuff.
So, I think, do the original atomic orbitals make sense?
The original ones
Okay.
make sense.
So the idea is this orbital has a certain shape. These orbitals all have different shapes and orientations. And when we have 2 atoms interacting, the way they interact is with their orbitals. So back in 221, we learned, oh, well, if something's going to interact with something else, maybe we need to hybridize, mix orbitals together to create new shapes to make them have the right orientation. This is a different way of looking at bonding. So instead of thinking about it as a structure like, oh, how am I going to make this connection? Instead, we look at just purely energies. So we say, oh, this has a low energy, these have higher energies relative. And then we have another atom that has the same orbitals with the same energies. And orbitals that are similar in energy will interact, and they'll mix together mathematically.
Okay.
And the rule is, for every pair, or every 2 orbitals that overlap,
It's the
I
same.
get a pair of new orbitals called MOs, molecular orbitals. And one of them's bonding, the other one has to be antibonding.
Why? Does not have to be.
Well, so look at the energy. So these are the same energy.
Yeah.
The new bonding orbital is lower in energy. Well, you have to have the corresponding raise in energy for the other orbital. Because
To
you
make
don't
it
get
look
energy
awkward.
from nothing. You're not like, yeah. So the bonding MO is lower in energy, but then the antibonding MO is higher in energy on it. So these average out to be the same as these basically.
And then I forgot how to tell like if it's pi or sigma bond, and like why do you even need to write that?
So because it's so mostly because of the p orbitals, you have to distinguish what kind of overlap it is. So you could have 2 atoms. So let's say the atom oxygen here and oxygen here. Well, this oxygen atom here has a p orbital that points that way, and this one has a p orbital that points that way. These 2 p orbitals are oriented in a way that they'll overlap in one spot. That's a sigma bond. But they also have orbitals that are going this way, and this one will have an orbital going that way. And then they'll overlap in 2 different spots, side to side. That's a pi bond. So that's where these come from. So these 3 p orbitals and these 3 p orbitals, well, one of each of these is pointing like that, and they're making the sigma bond, and then the corresponding sigma antibond. And then the other 2 are pointed parallel like this. They're doing side to side, and then there's another ones that are going this way. And so that's where these 2 come from, and then there's the corresponding antibonds. They go with those.
Okay. Well, so
And then notice 1, 2, 3, 4, 5, 6 atomic orbitals. Those mix together to make 1, 2, 3, 4, 5, 6 molecular orbitals.
Okay, that makes sense. But what if like, how do you know? Like, how did you know that? Oh, I guess never mind because it just has to. Like, I was gonna ask, how do you know which one is in the middle, or should be paired and not paired?
Oh.
But you have to fill up. that why?
You mean here, like this?
Like, why are those two unpaired and those?
So
right here and
it's because the oxygens come with 6 valence electrons each, and if I add two times 6 is 12 electrons, and I start from the bottom. The electrons have to go to the lowest energy orbitals possible. 2 electrons per orbital is the rule.
Yeah.
So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and the last 2.
Yeah, you have
If
to.
they're the same energy, Hund's rule, I need to put 1 in each degenerate orbital first.
Okay, I was just, yeah, I knew that, I was just wondering.
That's
like,
fine.
If you had to, I don't know. But so, Sunflower's MO diagram also is the same as orbital, like you have to fill up the lowest ones first.
Yes.
Okay.
Yeah, and this pattern is exactly the same for oxygen, for fluorine, for neon, and for most of the higher level elements too. The only one that's different, and I think this is in the workbook and the book, is for boron, carbon, and nitrogen, the really small, not small, low, I mean, they're pretty low in atomic number, but for boron, carbon, and nitrogen, these two swap spaces, like the energies are different. But that's it, and like I said, I would give you everything, I would give you where these lines are. I just wouldn't label these, so I wouldn't put this as 2s, 2p, sigma, pi. You'd have to label it yourself.
Okay, we have to label it sigma.
But the bonding orbitals always come lower in energy than the antibonding orbitals.
But,
okay?
so you're saying the sigma and pi stuff is usually gonna be the same as.
Yeah, and you can tell the sigma. The sigma is the one by itself. The pi comes in sets of 2, right?
okay.
Because there's the pair that go this way, and there's the pair that go this way.
Okay.
So they're always going to come in sets of 2.
Thank you, that makes so much more sense. Okay, thank you so much.
Uh-huh.
Oh, our quizzes?
Forgot about that. Yeah, I can go grab them.
Thank you so
Mhm.
much.
Anybody else want their quiz? Or not? Oh, you're in a different class. That's fine. Oh, yeah. I can grab yours though if you want.
I just had a question. I think I left my headphones in the office hours, maybe.
Oh, in the lab?
Yeah.
Yeah, we can go check.
Okay.
What's your name again?
Daisy.
Daisy, that's right. Any other questions about chemistry? Alright, so let's put this away real quick and then I can take you over.